So, good evening, everyone. Today would be your technically the last class uh, where I will be teaching. In the next class, we'll be having what you call this revision class. If you have any doubts, we can discuss in the next class, and I'll be discussing about the question paper pattern. Okay. So, today I'll be talking about this application of biomedical signal processing. In the last couple of days where you have given this flipped class lectures, so over there many of you have summarized many of the things. So I herein what I will do, I will be just going pretty fast so that I can complete this slide today itself. Okay, so please be patient with me, and if you feel that you want me to explain something in depth, you just raise your hand and just ask me, so, please explain this. Okay, otherwise I'll be moving pretty fast. Okay, so let's start with this topic, applications of biomedical signal processing. So we have already seen in the last few classes what are the different biosignals, biomedical signals in fact, ECG, EEG, EOG, EMG we have discussed. Then there is another signal which is called phonocardiogram. As the name suggests, phono, then cardiogram. So cardiogram, it is associated with the heart function. And when you add phono, that means it is related with the sound. So recording of the sounds of the heart muscles or the heart, it is regarded as phonocardiogram. You must have seen the doctors, they are putting up the stethoscope and they are hearing the sound of our heart, right? Now, if you just make it in an electronic format and if you can collect those sound signals, so what are sound signals? They are nothing but some signals, right? So if you collect those signals and record those sound signals of the heart, then it is regarded as the phonocardiogram. So then someone talked about this electrocorticogram, right? So these are some of the common biomedical signals. Okay. Now, when we talk about the applications of the biomedical signals, we are in general we are basically talking about five main categories. The first one is medicine. Why we collect the signal? We want to analyze the biosignals to know whether any pathophysiological condition is there or not. Then based on that, what we can do, we can go for the medication, right? So in the medicine, so then we have, as I told you, we can use it for the disease diagnosis. Then we can use it for understanding the human psychology and behavior. It is associated with the EEG signals. Okay, then we can devise some smart devices to analyze the biomedical signal processes, and then we can use the biomedical signal for rehabilitation purposes to control some devices. Okay, now next is your this application of the speech signal. Speech signal is another kind of biomedical signal. The reason being, depending upon our voice, uh, the nature of the voice, we can say whether there are any disease or not. Say for example, whether we have some cold or not, whether there is any infection of the pharynx. Okay, so we what we call as the pharyngitis and all these things. So we can diagnose many things. Then we can also use this voice signal to control the rehabilitative devices. Okay, have the voice signal, then we can apply some processing techniques over here. Okay, so these are the processing thing. Then from here we can generate the control signal, right? So you can also put a switching device, because when we speak, what happens, the device or the rehabilitation device what you are designing, it may think that you are trying to communicate with the device. Okay, to avoid that, we can have a switching device from here. So from here we will be having a comparator and it will give an output to the AND circuit. So when you are having this control signal and when you have put this switching device on, then only this AND gate, it will send a control signal to the rehabilitative devices. Okay, So herein what we have done, we have taken the voice signals, we have processed it, and after the processing we have categorized into high level, medium level and low level commands. Okay, accordingly if you see there are three LEDs. So for the high level, LED 1 was glow. In the second level, LED 2 was glow. In the third level, low level, LED 3 was glow. Okay. So now after doing this, if you see, we have got an idea that we are able to generate the control signal in a proper way. Okay. Now what we can do is that we can send these control signals to the rehabilitation devices through the Wi-Fi device. Okay, through the Wi-Fi device. So herein, basically instead of the Wi-Fi, we used Zigbee communication protocol to transfer the control signals to the other device. Okay, so herein I will show you one video. It is not the direct representation of this one, but mm, we what I will be showing is that the control of a robotic arm using the voice command signals. Okay, which is similar to this one. So here I have given a summary. So basically what we have, if you see, we have a signal acquisition and classification module over here. Okay, then we have a servo motor control module. Okay, so how do you use to communicate between these two modules? Because when we have this signal acquisition and classification module, it will acquire the voice and it will generate some command signals in the form of 0 and 1, right? Now it has to be transferred to the device in a wireless manner. So for transferring that into the other part of the device or the other module, the servo control, this motor module, so you need to have an wireless transmission. So if you see, there are majorly two modules. One is signal acquisition and classification module, and the other is the module where, or rehabilitative device module, where the device will be working as per the voice command of the user. Okay, yeah, it should work now.
Activate. Base left. Stop. Base right. Stop. Shoulder up. Stop. Shoulder down. Stop. Elbow up.
So if you see, there are various servo
Stop.
geared motors are there.
Elbow
You
down.
can control these geared motors using the voice command.
Stop.
So it all depends what you want.
Wrist
The thing is
up.
that it should be clear to your mind
Stop.
how you are trying to generate the.
Wrist down.
In our case,
Stop.
the classification module, it was the highest amplitude. What was the peak amplitude? So in the high was more than 1800 unit, medium was 351 to 1799 units, and low was 100 to 350 units. Okay, so accordingly we have designed the module. So it is a one of the simple case of artificial intelligence. Okay, you are not putting up any what you call any high level algorithms, but just defining the ranges, you are able to generate the control signals, right? Now next is application of the speech signal. So where we can devise a voice control home automation system. So uh, how you can do it? Here is the block diagram. You have a Hall effect sensor which is connected with the Arduino, which is basically the microcontroller, and it will take the decision on behalf of you. Okay, so this Arduino is again connected with a Bluetooth module, which will be connecting with the mobile phone. Okay, now this Arduino, it will again give instruction to two terminal devices. Okay, so what how you can control these two things? So you initiate a magnet, you take a magnet near to the Hall effect sensor, it will generate a signal of 1. So it will, this Hall effect sensor, it will basically be acting as a switching device. Okay, as it activates this one, so switching device, it will give a signal to the Arduino. That signal will be communicated to the mobile through the Bluetooth module. Okay, so as this activation signal is sent to the mobile, the Google speech recognizer, it will be activated, and then you have to speak the command over here. So once the speech is being recognized by the speech recognizer, it will send the command text to the Arduino through the Bluetooth module. And over there, you have the information over there, what you want to do with the terminal devices. Then accordingly, it will turn on the devices. Okay. So this is the uh, app which was developed. Okay. Now let's look into the demonstration.
This is a prototype voice controlled home automation system designed for locomotor disabled subjects. The system primarily consists of the Arduino board and its related program, the specifically designed printed circuit board for the circuit, which mainly consists of the Hall effect sensor, the HC05 Bluetooth module, the interconnection ports, indicator LEDs, and the USB port for connecting the loads. It also consists of the Android app specifically designed for this application. How the system works is that when I move a magnet in the vicinity of the Hall effect sensor, it generates a signal which goes to the Arduino board. On receiving the signal, Arduino board issues a command which goes to the Android app via the HC Bluetooth module. On receiving this command, the Android app launches the speech recognizer, and now the subject can speak his command into the app. This command is then converted into text, and this text is again sent back to the Arduino program via the HC05 module. Here the Arduino program ascertains what command has been received and then takes the corresponding action. We should have a small demonstration. All on. As you can see, on receiving, on activating the system and giving a command, the system recognized the command and the loads were made on. Now, on giving the off command, the loads should go off. All off.
So you can see, just by using this speech signals, we can do the thing here. He has just shown the demonstration that both the devices are getting on at the same time and getting off at the same time. But you can mm, control these devices individually also. Okay, just you have to develop the logic within this Arduino microcontroller, what you want to do with the device, right? So the summary has been given over here. You can look into that. Then coming to the EOG signal processing, again, if you see, we have this signal acquisition module. You place the electrodes, you acquire the signal. Then after the acquisition, you do the filtering. Okay, after the filtering, you go for the signal classification, and then lastly, you go for the application to control the rehabilitation aids. Okay, so this is the module over here. So you are having the electrical electrode for the horizontal signal, electrode for the vertical signal, as it was discussed in the EOG acquisition by one of you. that we can place the electrodes either in the gantry positions or in the orbital positions, right? So from these two channels, you can acquire the signal and then process it and then develop a logic to control the rehabilitation devices. So again, before we go for the what you call controlling a particular device, we have to look into whether whatever the logic we have designed, whether it is working properly or not. So here, if you see upon the movement of the eyes in particular directions, you can see the LED, different LED lights, they are being glowed. Okay, so let's look into the demonstration of this device.
Starting from zero in JavaScript can be harsh. Zero experience.
Start. Forward. Stop. Backward. Stop. Forward. Stop. Left. Stop. Right. Stop. Backward. Stop. Forward. Stop.
Okay. So here is this summary. So how the device works. This is for your exam purposes. You can look into that. But it should be similar for all the systems. Okay. So then we have the differences between EOG, ECG, EMG, EEG. What are the critical differences? You should go through this. You all have already discussed, so I'm not going into it. So then this is about the EOG. What is the definition? What is the voltage range? Okay, because as I told you, this EOG, it is basically the corneal retinal potential difference, right? So the generation of EOG signals is different as compared to the other types of the signal. Then why this difference? This difference is due to the metabolic activity of the retinal cells. Metabolic activity of the retinal cells, right? So key difference between the differential amplifier and the instrumentation amplifier. This I intentionally kept it even though it is not a part of the BSP. The reason being, as I have seen that many of you do not know what is the basic difference. The thing is that if you compare both the amplifiers, this is a difference amplifier, differential amplifier by default. Okay, what it does, output is directly proportional to the V1 difference V2. Okay, similarly over here also your output is directly proportional to the V1 difference V2. Okay, so there is no what you call, if you, if someone says that it, someone said right that one is a difference amplifier, the other one is not a difference amplifier, that is incorrect. The thing is that both are difference amplifier, but what is the advantage of the instrumentation amplifier? Basically in biopotential amplifier we use instrumentation amplifier with subtle changes. Okay, so I am not going into that part because that is the that should have been covered in your biomedical instrumentation class. So what is the difference? The difference is into the input level. If you look, over here, if you consider as section A and section B, so section B and the differential amplifier both are same. Okay. Where is the difference? The difference is in the input stage. Okay. So in the input stage, what happens is that if you look into the input, it is directly going into the non-inverting terminal. Over here also, it is going into the non-inverting terminal, and they are directly getting into the op-amp. And what is the input impedance of the op-amp? The input impedance of the op-amp, ideal input impedance, it is infinity. So that means no current will go through. No current will go through into the system. So what does that mean? What does that mean? Have you heard of this loading effect? Loading of the circuit? नहीं सुना है? Okay, so it reduces the loading effect actually. When there are no current passing through, then you will be having you can stop the loading effect. In a simplest case, if I give you, say, suppose there is a voltage source, okay, and there is a resistance, say 100 ohms, okay. Now, if you put a series resistance of say 10 ohms, and this 100 ohms is our the 100 ohms, it is our what do you call, uh-huh, the 100 ohms is our say appliance resistance, okay. And if you look into here and if you try to measure the voltage across it, so what will happen? Since this resistance is quite low, even the total resistance is quite low, the current will be passing through, okay. So V equals to IR, okay. So what will happen? I, it will be equal to V by R, okay. So I is equal to V by R. A lot of current will pass through, and when it will pass through, the voltage drop will be, it is high means voltage will also be high. Now if you increase this to 1 gig ohms, what will happen? Almost limited current will be passing through, okay. And since there will be only a low amount of current will be passing through, the voltage drop across this resistance, it will be very high, okay. In total, basically in total it will be very high. So what it is doing in the first case, since lot of current is passing by, so the voltage drop, it will voltage drop, it will be quite larger. And since the voltage drop will be quite larger, the signal what you want to acquire, you will not get it to acquire, you will get a lower voltage. On the other hand, when you have a very high resistance, almost no current will be drawing drawn through the circuit, and you will be able to get the high high voltage. Maybe, sorry, no, it is not in the series, sorry, not in the series, yeah, it should be in, because this is in parallel, na? So because the voltmeter what we use to measure, we use it in parallel, right? So this is your, say, 10 ohms, and that is your E. So when you have this, so the voltage drop will be quite minimal across this resistance. That means we are losing the voltage information. However, when we are having this 1 giga ohms, the voltage drop will be quite larger. Okay, so you will be able to measure whatever the source voltage you are having. So the basic funda is that what you are measuring, V output is directly proportional to the V2 difference V1 or V1 difference V2, right? So basically you are measuring the potential. So your input impedance should be very, very high. And this is what it is happening over here. Since your voltage is directly getting into the non-inverting terminal of the amplifier, the input impedance is getting very, very high. And hence the voltage signal loss, it is quite low. Okay. On the other hand, if you look into the differential amplifier, if you look into the input impedance, it becomes R plus R over here. Current can pass through. Similarly, over here also the current can pass through. So the input impedance of the differential amplifier is what you call it is legible, or it is infinite and finite, right? So it is finite. So since the voltage is this resistance is finite, that means the input impedance is finite, and hence there would be a loading effect. There would be a loading effect, and due to that you will be losing the current. And in the case of biopotential signals, what happens is that our biopotential, it is either in the microvolt range or in the millivolt range. So you need to first, what you need to do, you need to ensure that there is no further drop of the voltage, and secondly you should get a proper amplification of the voltage. Okay, now proper voltage or the loss of the voltage can be minimized by using the instrumentation amplifier. And further, if you look into this resistance factors over here, so all this resistance gives to first stage and second stage gain. Okay, so combinedly, gain of first stage, if you say A1, and this is the gain of the second stage A2, the combined gain would be A equals to A1 multiplied by A2. Okay, because this becomes two cascaded systems. That's why A1 multiplied by A2. So because of this reason, your gain of the biopotential amplifier, it increases in a drastic way. Okay, so this is the advantage of the instrumentation amplifier over the differential amplifier. And I also asked about the common mode rejection ratio. What is common mode rejection ratio? The common mode rejection ratio can be found out for any differential amplifier where we are giving basically differential inputs. So what we do, first we give a common mode gain, common mode input. Common mode input means same input. Say for example, if I give 1 millivolt to both the terminals, okay, so we should get some output. Ideally we should not get, because our output is directly proportional to V2 difference V1. So it should be, ideally it should be 0. But the problem is that when we talk about these resistances, they are not idealistic in nature. So they are non-ideal in nature. So we will be getting some output. Okay. And then, so when you give a common mode signal, so it is called ACM, gain for the common mode. Okay. Similarly, when we give VA and VB, we will get another output. So that is a differential gain. That is a differential gain, and it is called AD. Okay. Common mode rejection ratio is nothing but true. CMRR, it is given by AD by ACM. Okay. So CM should be ideally 0. So CMRR should be ideally infinite. Okay. CMRR should be ideally infinite. So higher the CMRR, the better is your uh, construction of the differential amplifier. It can, this CMRR is also true for the differential amplifier. Okay, please bear this in mind. Now coming to this application of the EMG signal. Similarly, we can acquire the EMG signal, we can process the EMG signal, and after processing the EMG signal, you develop some logic to develop some control signal, and using those control signals, you can use it for controlling a device. Okay, so let us
middle section, corner section, all the section.
so the summary has been given, so you can go through it. But the main thing is, see, in all the cases, we have a signal acquisition come classification unit. We have another unit. Say for example, it may be a robotic vehicle, it may be your robotic arm. Okay, whatever the rehabilitation devices. So you can say rehabilitation device. Okay, now you have this signal acquisition come signal classification unit that will be used to generate some control signals. Now those control systems will be used to control the movement of the rehabilitation devices. So this is the basic logic by which you can use any of the biomedical signals except the heart signals to control any device. Okay, whether it is speech signal, whether it is EOG, whether it is EMG, whether it is EEG. Okay, so the summary has been given. So slightly different method you will find it in the ECG signal. ECG signal, we basically use it for this classification purpose, specifically what type of disease we are having that we want to find out. Okay, so if you see we have the ECG signal, then we do the pre-processing. After that, you go for the heartbeat segmentation, then you go for the feature extraction, and then we go for the what type of disease we have. Okay, so when we talk about the features, features are basically categorized into these four types. So first is lower order statistical features, higher order statistical features, entropy based features, and miscellaneous. In the lower order statistical features, we have arithmetic mean, we have median, we have variance. Okay, then higher order statistical features, we may have kurtosis, we may have skewness. Then entropy based features, we may have log energy entropy, we may have Shannon entropy, we may have Rennie entropy, we may have Sally's entropy. In miscellaneous category, we have trigger energy. Okay, so these are some of the features. Okay, so again, when we talk about this Sally's entropy, trigger energy, there are some parameters what you can change, and by changing those parameters, you should be able to generate Sally's, a series of Sally's entropy or a series of trigger energy. Okay, I am not going into the details of that one. Okay, now coming to the statistical analysis, in the last class, Biomedical has given you a nice demonstration how to analyze the data, and the same thing it comes over here also. Okay, so you get the feature set. Okay, then you perform the normality test. From the normality test, you can go for the Shapiro-Wilk test to find out whether your data is normal or non-normal. So when we start with the Shapiro-Wilk test, we assume, our assumption is our data is non-normal. Okay, that's why when we choose the p-value, when p-value is less than 0.05, we consider the data to be non-normal. Okay, this is slightly different. This you need to understand. Okay, so if you see, if p-value is less than 0.05, we have the non-normal distribution. So if it is non-normal distribution, we go for the Wilkinson sign rank test, and from there again, if you find out the p-value, and from there you can find out the statistically significant features. Okay. Now, if your data is normal, then you can go for the two pair t-test. Over here we are talking about the only two classes, and if it is many classes, then we go for ANOVA followed by post-hoc Turkey test. Okay, and on the other hand, instead of the Wilcoxon signed rank test, only in Wilcoxon signed rank test, we go for the Wilcoxon signed rank test with Dunn's post-hoc Dunn's test. Okay, so please keep this in mind. Over here, this chart was made by my student, wherein he was having only two classes, and hence we have given this chart. So from here, you can find out the statistically significant features. So you can use these features for further classification to develop your this classification model. Okay, so this is the simplistic model. Now there are many AI based systems also, where you can find out in an iterative way which features they are significant. And I hope in your AI class, Khalid sir must be teaching you how to find out the this important features, right? So I'm not going into that thing. There are feed-forward networks wherein you start with one feature, then you start to add different features again, and in that way, you try to find out which set of data will give you the best result, or which set of features they are the best features for classification. Okay, so it is all AI based, so we call it as feature uh, selection method. Okay, automated feature selection method. Okay, when we have this when we talk about automated feature engineering, then we are having two categories over there. The first one is the automated feature generation. Okay, suppose you are having features say A, B, and so on, which I already told you in one of the classes, that taking the existing features, it will do various permutations and combinations. Say for example, A by B, or log of A by B, or log of A, or exponential of A, right? In that way, it will generate features. Okay, so first one is the automated feature generation, and the second would be the automated feature selection. Okay, in the automated feature selection, there are two methods again. There is feed forward method and there is feed backward method. In feed forward method, we start with one feature and then we start to increase the thing. And backward method, we take the whole of the data sets and then we start going backwards, reducing the data set. Okay. However, in general, feed forward network algorithms, they are more preferred. Okay, in R&D for R&D purposes. So, so we have talked about this automated feature engineering, and over here we are having automated feature generation and automated feature selection. So again, next I will give you an example of one of the students who worked on how the coffee can affect the autonomic nervous system. Okay, I'm not going into the details again. So you must have heard of RR intervals. What are RR interval signals? We have talked about the different QRS complexes. The time duration between these two peaks, it is regarded as RR interval. And when you get a series of RR interval, consecutive RR intervals, then it is called RR interval signal. Okay, or heart rate variability signal. So once we get this heart rate variability signal, then we apply an averaging filter to get the average envelope of the signal. So you get this red line, which is the average of the other intervals what you have got. And now this signal, it is used as an analysis tool for further prediction. Okay. So over here, we get a lot of features. Say for example, VLF, LF, VLF is very low frequency, LF is low frequency, HF is high frequency, LF nu is normalized low frequency. Similarly, we get this HF nu, VLF percent, LF percent, HF, and LF by HF ratio. Now, why these other interval signals are pretty important? This is because the heart rate variability, because this other interval signal, it gives you a measure of how dynamic your heart is behaving. Okay, if the dynamicity of the heart is seized, that means you are having a serious heart problem. Okay, say for example you are sitting, now suddenly you start running, then as you start running your heartbeat should increase. Okay, then again when you are sitting down your heartbeat should come down to its normal basal level. Okay, so if you see, heart is not a static system, it is a dynamic system. Even when suppose you are sitting over here, now if you are sitting over here, somehow you hear about a very good news, your heartbeat will change. Okay, again if you hear a very bad news, it may change. Okay, again even if you have not done something, so what happens, what our nervous system is trying to do, it is trying to maintain a constant heart rate. Okay, but within that heart rate also, within the millisecond time also, you will be getting some dynamicity. So you must have all heard of these control systems, especially the instrumentation engineers. So what happens? So the control system, it tries to predict what is whether your say output it is increased or decreased. If it has increased, in the next cycle it will try to decrease it. Okay, and vice versa. The same thing it happens with our autonomic nervous system also. Okay, so over there again, if you see there is a dynamicity. Now, if this dynamicity is lost, that means you are in serious trouble. Okay. So over here you can find out all these features. Okay. Now, once you are getting all these features, so in the softwares you will get this kind of thing. You will get all the values once you put in the other interval values. Okay. Now from there you can find out the important features. Over here if you see, we have found that VLF power, LF nu and LF by HF ratio, these three are the statistically important features. Okay, now what we saw is that LF nu power decreased. This indicates a reduction in the sympathetic activity. So if the LF component is reducing, it is regarded as the reduction in the sympathetic activity. VLF power, it is usually not assessed using the short term recording. Okay, so in our case we recorded it for 5 minutes, so it will be regarded as the short term recording, so this cannot be used for the analysis. Coming to the LF by HF ratio, a decrease in the LF by HF ratio was seen. That means there is an increased parasympathetic activity after the consumption of the coffee. Okay, so in short, if you see, consumption of coffee is associated with reduction of the sympathetic activity and a corresponding increase in the parasympathetic activity. Okay, so in this way you can try to relate the physiological aspects of your organs using the signal processing techniques. Okay, so then again we can understand the brain activity. You have already carried out this experiment on VEP. There is another method which is called SSVEP. Okay, SSVEP means steady state visually evoked potentials. Okay, so in VEP we are basically changing the patterns. Okay, there is a change, cyclical change in the patterns. However, over here, so change in the pattern means we are giving it 2D input. Okay, we are giving it 2D input. In the case of SSVEP, we are giving a 1D input, that is the flickering of the light. Okay, so we can control the flickering of the light, right? Now it is cyclical in nature. When it is flickering, it will come up, come down, come up, come down. So it is having a frequency. Our brain waves, they are associated with frequencies, right? So When we do that, what the SSVP signal does is that in our brain also, within the EEG signal, we will be having cyclical patterns, okay, which will be superimposed within the signal itself. So we will not be able to find out in under general analysis. Okay. So what happens is that if you are giving a 3 hertz stimulus, then within that signal there would be a hidden 3 hertz signal. If you are giving 10 hertz signal, flickering signal, then within the EEG signal there will be a superimposed or hidden 10 hertz signal. Okay, so this is the basis of SSVP signal. On the other hand, in this thing, VP signals, what we are doing, we are giving a 2D image and we are looking into how the higher order functions they are behaving. Okay, the neural pathway actually we are looking into the thing. Now we chose 7 frequencies. Why these 7 frequencies they are important? This is important because we are having the frequency bands of delta, theta, alpha, low beta, beta, high beta, and low gamma. Okay, and what we did, from each of these frequency ranges, if you see the frequency ranges have been given, we have chosen one frequency each and we have tried to excite the brain using those frequency components. Okay. Then from the electrodes, whatever the amplitude values you are getting, you can do a brain mapping. You can do a brain mapping. Okay. So which part of the brain has been activated the most? Okay. Now, as in anything, we do the pre-processing, then SSVP detection. Over here, CCA canonical correlation coefficient, uh, uh, canonical correlation activity it is being used to determine the coefficients. So from those we can find out which region of the brain can be activated. So I'm not going into the details of this one. So again, we can find out the feature extraction. You may not have heard about this recurrence plot. If you see we are having the recurrence plot. So it is another uh, type of statistical analysis where we can get statistical parameters and it comes under the miscellaneous category. So from there also we can get the different features. Okay. So as I already told you, signal processing and classification, it is all about the features. So what are the features or what are the informations hidden within your signal that has to be extracted out so that you can do an analysis and find out what is happening physiologically if you want to go for the diagnosis, or whether you can use those features to control some rehabilitation devices. Okay, so again you can go for this statistic not statistical this AI based analysis, and you can go for the this classification. Okay, so this is what it has been done. So with this we complete this chapter. We complete our today's class. Okay, so this study was being done by one of the MTech students. Currently, he is doing PhD in IIT Bombay. So, yeah, this CCA, canonical correlation analysis. Yeah. So, this ECG classification, it was done by one of my PhD student. This was also done, basically done by 2 students. First initiated by one of the BTech students, and then one of my PhD student continued with that. This one was done by one of my PhD students again. This was this one, it was done by one of the MTech students. This one was done by, I think, MTech, or no, PhD student. Yeah, but yeah. So if you look in all the aspects, my only thing is to show you is that whatever the signal it is, and for whatever purpose you want to use it, the main thing is that you have to acquire the signal, you have to pre-process the signals so that the, the noises and other artifacts they are removed. Then you have to develop a logic to classify those signals. Okay, suppose if you want to control any assistive device, those control signals or the classified signals will be used to control the devices. If you are trying to go for the diagnosis purpose, disease diagnosis purpose, then you have to again classify the thing, and from the classification you have to tell that this is this disease, this is that disease, this is that disease. Okay, so if you see, the classification is also nearly same, only the application part it changes. Okay? So this is the power of your signal processing technique, right? So that's it from my end. Anything? क्या हुआ, इतना सीरियस हो जा? हंसना है तो खुल के हंसो. No? The only thing is that